Tes. Good morning, everyone. So we met again. Uh, I just get info that today's lecture is about seismic attributes and seismic geomorphology, and there is some misunderstanding about the schedule. So now I have to give you these topics for you, and then fortunately I also did this topic 2 years ago, so I have it in my PC. So yeah, in this next 2 hours we will discuss about introduction, I would say, because we didn't get much into detail. So we will mostly discuss about the application of these seismic attributes analysis and seismic geomorphology. So I know that some of you choose seismic attributes topic, and also for others group also need to utilize this seismic attributes analysis. So it's beneficial for your project. And I think in the next session I will discuss about how to implement this attribute and seismic geomorphology in Petrel. Okay, so as I always said, uh, seismic interpretation is not about drawing the line. And in this lecture, actually, we will utilize how this seismic can inform you about geology, geophysics, and reservoir stuff. So it's not about drawing the line, it's about extracting the geology, geophysics, and reservoir information out of your seismic data. So today's outline, I divided into three. So first is about the definition of a seismic attribute. What is this guy? And then the second one is an overview of seismic attribute analysis, and then it's including in seismic geomorphology is including on the qualitative part of the seismic attribute analysis. So that's why we put this course together. And the last one, we want to have some thought about the quantitative approach in this seismic attribute analysis. So this is the outline for today's lecture. So what is the seismic attributes? So in simple terms, this seismic attribute is a mathematical approach on your seismic trace. That's the simple one. Of course, you can have different definition from different people, but the general definition is this mathematical analysis of your seismic trace. So, for instance, if you have this trace, So it's just about mathematical approach of your peak and your trough. Because your peak and trough will represent something about geology, geophysics, and reservoir. Okay. And then classification, I think it's like almost every year they found a new seismic attribute. So today we have like hundreds or even thousand seismic attributes, different type of seismic attribute, and it's increasing every year. So we will discuss after this. Is this useful for us? Because sometimes it's just redundant and useless. So it depends on what is your objective. Like for instance, in this project, what is your, so I always say, what is your topic? Because then we can relate which one is useful for our topic, not for other topics. I don't want to discuss about this. This is too much. And also, even in Petrel, they have you seen this poster? I put it in the blackboard in the courseworks and project, and there is a recommended seismic attributes. So even Petrel, he make their own. He make his own recommendation. Like if you work in this fracture indication, so you can see some attributes that may be useful for this fracture indicator, but not the others. So it's a lot of seismic attributes. And as I said, as this guy said, many seismic attributes are redundant or useless, and sometimes it's confusing us. Is this the real geology, or is this just some artifact? But some attributes are useful for sure. So we just need to uh, know about our objective in our works. And this is the most important things in seismic attribute analysis. It's about polarity and phase. So phase and polarity is important. So not only in seismic attribute, but in the whole seismic interpretation, to know the phase and polarity is important, because then you can relate it, the impedance of your seismic trace into the geology and geophysics. Remember, if you don't know about so for instance, if you don't know about the phase and polarity of this trace, then it's quite challenging to interpret geology and geophysics. So phase and polarity is important. Um, and about the polarity, it's about the convention. So it's about the agreement between geophysicists. And then sometimes it's confusing because they have SCG, American, or European convention, and also sometimes they put colors in this convention. So if you read somewhere, they put if in this SEG or American polarity, this increase in acoustic impedance is represented by red color. But if you go to your seismic template, you can change your color into black and white, or red and blue, or yellow and black. So, so my suggestion is just use the seismic trace, not the colors, because it will confusing you. So it means that in the so if you just use seismic trace, it means that in American polarity or SCG polarity, an increase in acoustic impedance is peak. That's all. This one is much more easier. So in SCG polarity, increase in impedance represented by peak. Decrease in impedance represented by trough. That's much more easier. And the phase convention, zero phase, minimum phase, that's just what you need to know. Because remember, this interface is represent your rock boundary, right? So if I put, if it is zero phase, so it means that if you have a lithological column like this, It means this is this boundary. So for instance, if this is shell, and if this is sandstone, so the phase is this interface. And you remember that in this lithology, we have density and velocity. And here, we also have density and velocity. And the importance of seismic attributes is this guy. So remember my my favorite motto: seismic interpretation is not about drawing the line. And also here is the same: is to extract the most information available from the seismic response. So seismic attribute is useful to extract most information from your seismic data: lithology, fluid, stratigraphy. Even we discuss about how to extract relative sea level from your seismic data. Do you remember? And even we can create chronostratigraphy chart from your seismic data. So that's what we need to do with our seismic. Try to extract geology, geophysics information from our seismic data, not only drawing the lines. Yeah, and it's including hydrocarbon evaluation, reservoir characterization, and this guy is much more in the petroleum geoscience stuff. Okay, so that's quite easy for definition of seismic attributes. It's a mathematical approach to your seismic trace, and it's useful to extract geology, geophysics, reservoir information from your seismic data. And next, about the seismic attribute analysis itself. So we divide it into qualitative and quantitative part. So in the qualitative analysis, or seismic geomorphology, so this is the 3-step on this qualitative analysis on the seismic attributes: data quality, for sure; seismic phases. In this case, we want to relate into the positional environment. Some part has covered by lecture 3, seismic phases analysis, and then some part I think we can discuss today. And the last one is about seismic geomorphology. So qualitative analysis, data quality, as we discussed early in our project, when you have your seismic, then you need to check the quality of your data. It means that you need to check the phase, polarity, your quality of your data, and also for seismic artifact, migration, noise, all this stuff. Because then, and also fluid indication, because sometimes your seismic response is influenced by fluid. It means that if you want to interpret the stratigraphy, for instance, you need to take out the fluid response of your seismic. Because if you go to your project in the upper part, when you have the erosional truncation, there is some fluid influence on your seismic response that make your seismic response will be blurry, and then your stratigraphy is not obvious on that section. So if you want to interpret the stratigraphy, then you need to take out this seismic response of fluid. Facies are package of rocks, yes, that exhibit similar characteristics like lithofacies, petrophysic, and depositional facies. And then this in this seismic attribute, in this qualitative seismic attribute analysis, this seismic facies means this one: amplitude, continuity, and frequency. I think Kamal has explained this in lecture 3 about what is the amplitude, continuity, frequency. Like here, frequency, This is not frequency of your seismic data. Like this is not hertz, but this is the frequency of your layers. How many layers do you have, and how often these layers appear in your zone, for instance. And then after that, all these phases will relate it to this one, depositional environment. And this is from lecture number 3. And this green table, that's the important aspect for this qualitative analysis of our seismic attributes. So it's because before, when we talk about seismic phases, we just talk about reflection termination, reflection configuration, external forms. But now, in this qualitative seismic attribute, we add more about reflection amplitude, frequency, and then velocity. And this is seismic phases, both in the qualitative seismic attribute and also this normal seismic phases. So this part here, where you have amplitude, continuity, and velocity and frequency, that's part of the qualitative seismic attribute analysis. I think we can try to interpret this section related to seismic phases on the qualitative seismic attribute analysis. So in this qualitative seismic attribute analysis, so what you need to interpret is velocity and frequency and amplitude. What else? Velocity, continuity, and continuity. Velocity of also, for if we choose maybe this one here, this divergent field. So what I can draw is this divergent field phases, something like this. So in terms of velocity, it can be anything, because the velocity is also influenced by lithology and also depth. So for the velocity, frequency. So this frequency is not hertz, but this frequency is how many layers in this zone, for instance. So if I compare this one and so maybe one more. So this may be chaotic. So in this case, this one is called as high frequency, and this one is low frequency, like that. So in this case, it's much more high frequency. But if you go here, where the reflector is mostly hammocky or chaotic, then this is what we call as a low frequency. Of course, it will be different from people, from one interpreter to another interpreter. So usually they will put a range, like here they will put high to medium, or this low to medium, because there is no exact answer on this interpretation. Amplitude is directly to your data. If it is bright, then it means high amplitude. If it is low, if it is like this, then it is low amplitude. So in this case, this is high frequency, and amplitude is high. Again, it's interpretation, high to medium, you can say. And continuity, you can see here, even though this has like a channel shape like this, but if you go to the right and to the left, the flank of the channel is just continuous. So we can say the continuity is continuous. And together with reflection termination pattern and reflection configuration, external forms, together with these two parameters, then you come up with environmental of deposition. So in this case, if you look at this divergent field, when you go up, you have some low amplitude chaotic reflectors that has some erosional stuff, this one, right? But if you go to this one, when the reflector is continuous again, so then you have some top lap or on lap maybe here. And if you go to the left, like this, the thickness of this zone here is thinner to this part, and you can have some downlap here. That's for a reflection termination pattern. And reflection configuration, what you can see here, since you have a thinner to this part and thinner to this side and thick middle part here. So you have something like, so if this is the base, you probably have something like this, right? You have a on lap to this side and you have down lap to this side, thinning to this direction, thinning to these directions. So this kind of reflection configuration. And then, so what do you think? What kind of environment is this one? So if I make another section, so it might be something like this, something like this. So what kind of depositional environment is this? Marine and regression, yeah? Or maybe just regression, because we can have in lake as well. So regression, that's a good point. Regression. It can be marine, or it can be lacustrine. Okay, so this is much more in 2D seismic approach. So next we go to 3D seismic. Yeah. This one, it can be vary, because it depends on the depth, and it depends also on the composition. Ferocity, you can say it can be vary. Okay, so it's 3D seismic. So in the 3D seismic data, this qualitative seismic attribute, it's almost they called as a seismic geomorphology. So it's the same. So basically, we want to take the seismic and then to interpret this paleogeomorphology at the depositional time. as you've seen in this picture, this is fluvial channels, this meandering sinuosity of the channels with this high amplitude in this channel system and this low amplitude in the surrounding. So this is what seismic geomorphology want to do. So you want to extract the paleogeomorphology. And after that, the and after that you can use, so for instance, if there is a wells here and then it contains some hydrocarbon, then you can calculate the volumetric from this seismic geomorphology. So this is a overlay between the seismic data and this modern analog in this fluvial and the shoreline system. So this is what we want to do in seismic geomorphology. So we want to interpret the paleogeomorphology at the depositional time, and also you want to correlate to the modern analog. So how it looks like today's. So this guy, Posamentier et al., Henry Posamentier and his friends suggest the workflow in this seismic geomorphology. First is to quickly scan your 3D seismic data by looking at inline, crossline, and time slice. And then look at for this, what he called as FLT, funny looking things. It means that it will relate to fluid or lithology. Okay? This is also part of the data QC. And the second workflow is to pick the horizon and subsequent illumination. So after you recognition this FLT, then you pick the horizons on that FLT, top and bottom or in this FLT. And after that, you extract the amplitude on that FLT horizons. So first is horizon. So if you have, again, this seismic trace, and then you interpret the peak, for instance, like this, 0 phase, then the workflow, the step number 3 is when you extract the amplitude at the horizon. So the amplitude at this point, okay? And then after you extract the amplitude, that's what they call as horizon slicing. So if you have, the horizon slicing means like if you have horizons like this. So this is horizon 1, horizon 2, horizon 3, horizon 4. So the horizon slicing, it means that you extract the amplitude at these horizons, at this point, at this point, at this point. Okay? And stratal slicing, so the other slice, so this is what we call as a slicing method. So you have horizon slicing, and then you have also stratal slicing. So in this stratal slicing, you divided the zone proportionally. So for instance, if I do the strata slicing in this zone, so the top of this zone is H2 and the base is H1. So what I did in the strata slicing is I take a proportionally like this from H2 to H1. That's what we call as strata slicing. yeah, or proportional horizon slicing is the same. And the last one, you also have what you call as time slice. So if you have this reflector like this is time, and this is the distance. So what you did is just slice through the time domain like that. But if your reflector is like this, then your time slice will cross all the reflector. So if you do time slice in this case, what you have is something like this. So it means that you will cross your reflectors. And then the next step is to do Fox body picking or to extract the geo body. Remember, you are working in 3D data, 3D seismic data. So when you have this horizon, strata, and time slice, then you can see, for instance, you can see some channels in your 3D, but then the background of the channels, which means like a low amplitude, is still there, right? So now, by using this Fox body picking or geo body, you take out the low amplitude value, which not represent your channels, and just stay the channels as a high amplitude. I can discuss this after in the next few slides. So later, what you have is just body of the channels or body of your reservoir. This is also beneficial for volume calculation because what you calculate in the volumetric is just the sandstone on the channels. Imagine when you're working in 2D lines, 2D data, when you have the zone like this is a top reservoir, this is base reservoir, and then for instance, you are working in this channel like this, they just use net to gross to calculate the volumetric, right? It means they just use proportion of shell and sand in the reservoir. But the uncertainty is still there. But by using this geobody, it means that you didn't calculate the shell. You don't need the net to gross because what you have is just volume of your sand in the channels. Okay? So if you work in the oil company and then if your boss give you 3D seismic data, then you need to produce this geobody of your reservoir. And then the next step is extraction of horizon best attributes. So this is, we implement some attributes in our geobody. And after that, we also implement, so this is the horizon-based attributes. So horizon slicing, strata slicing, time slicing. So this is the horizons attributes or surface attributes. If you later in the project, in Petrel, you can have volume, in the process panes, you can have volume attributes or surface attributes. So horizon or surface attribute, it means that you only play the attribute at the particular horizons. But if it is volume, it means that you calculate all your seismic data, 3D seismic data for the seismic attributes. So the result also a volume. And volume co-rendering, or they called also, today we call it as Rgb blending or spectral decomposition. So where we blend different frequencies from our seismic data to get much more clearer image in our channels, for instance. Even though there is no groups that choose this topic, the seismic geomorphology, But you can apply this seismic geomorphology approach in your project, like play and prospect groups. Who is play and prospect? You. It's also important to delineate the reservoir, because when you do the play and prospect assessment, it means that you need to come up with volumetric, right? And this seismic, since you have 3D seismic data, then the seismic geomorphology is a good tools for you. This is just some example of the seismic geomorphology from different setting, fluvial, self-age, and deep marine. There is a lot of example that you can find out about seismic geomorphology in different geological setting. This is just to show you that there is exists in every depositional setting. Okay, now we try to go to the study case about this seismic geomorphology. Any question? Now is 10:52. 8 more minutes to break. So, you have question? Yeah. For the slicings, so for instance, horizon slicing, you cut the layer on that horizons. So when you pick the horizons, you pick in the red pick or trough, you pick the horizon and you make a horizon in 3D. Then after that, the horizon slice is cut the layer only at the horizons. And if it is a strata slice, it means that you divide it, that so you slice the zone top and bottom, and then you divide it proportionally. So you slice on the imaginary horizons that proportionally divided the zone in the same thickness. If it is time, then you just cut the layer following the time domain of your seismic data. Like a Z in your, so in your seismic, 3D seismic, you have inline, crossline, and Z. That Z is the time slice. So when you show later in your project, you show the Z, then you have a image. That's image of time slice. Yeah. Oh yeah, this strata slicing is useful when you are dealing with hammocky or chaotic phases. When when it's difficult to interpret in every horizons. That's what we need in this strata slice. So how about your project? Is it okay? So the poster presentation will be April 8th, and then so you have like 1 month and 2 weeks more or less. So we hope that next week you are not working on the seismic well tie anymore, because this is just the small part of your poster. You need to go to the next step. Mhm. If there is no question, I think we can take a break for 15 minutes. So we meet at uh, 10, 10 sorry, 11:10.